December 7th, 1941. Pearl Harbor burns under Japanese bombs as Admiral Isoroku Yamamoto watches from the bridge of flagship Akagi. The surprise attack has crippled America's Pacific Fleet, but the veteran naval commander feels no triumph. His staff celebrates crushing victory while Yamamoto stares at intelligence photographs that keep him awake at night. Boeing B-17. Flying fortresses scattered across Hawaiian airfields like broken toys. Even damaged and burning, these four engine giants represent American industrial might that Japan cannot match. Yamamoto knows what his celebrating officers refuse to acknowledge. Japan has awakened a sleeping giant whose production capacity will soon dwarf the combined fleet's ability to project power across the Pacific. Within months, American factories will be rolling out B-17s faster than Japanese shipyards can launch destroyers. The mathematics are terrifying. Boeing produces one flying fortress every 90 minutes. Mitsubishi's most advanced bomber takes 6 months to complete. 3,000 miles away in Tokyo, another kind of mathematics consumed the attention of Colonel Takeshi Yamamoto. No relation to the admiral, but sharing his analytical mind and growing dread about American industrial supremacy. As Chief Procurement Officer for the Imperial Japanese Army Air Service, Yamamoto studied captured B-17 technical manuals with the obsessive intensity of a man searching for salvation in blueprints and performance specifications. The numbers told a story that military leadership refused to hear. Maximum bomb load 4,800 pounds carried to targets 2,000 miles from base. Service ceiling 35,600 feet beyond the effective range of most Japanese fighters. Defensive armament of 13.50 caliber machine guns that could shred attacking interceptors with concentrated firepower. Most significantly, structural design that allowed flying fortresses to absorb incredible battle damage and continue flying when Japanese bombers would have disintegrated under identical punishment. Colonel Yamamoto had witnessed this durability firsthand during the Doolittle raid when B-25 Mitchells, launched from aircraft carriers, demonstrated American engineering philosophy that prioritized crew survival over weight optimization. Japanese bombers were delicate instruments of precision warfare, but American aircraft were flying tanks designed to complete missions despite mechanical failure, battle damage, and pilot error that would do more elegant designs. The solution seemed obvious to Imperial General Headquarters. Japan would copy American bomber technology, reverse engineering flying fortress capabilities while adapting designs for Japanese manufacturing constraints and tactical requirements. Military leaders who had dismissed American engineering as crude and unsophisticated suddenly demanded Japanese versions of Boeing's four-engine masterpiece. The project began in January 1942 at Nakajima Aircraft Company's sprawling Musashino plant outside Tokyo. Chief Engineer Kenichi Matsumura received orders that carried the weight of imperial desperation disguised as technological ambition. Design and produce a strategic bomber equal to American B-17 performance within 18 months. No excuses, no delays. The Emperor's forces needed long-range striking capability immediately. Matsumura understood the magnitude of what his superiors demanded. 25 years of aircraft design experience had taught him that successful engineering required more than copying external appearances. The B-17's capabilities emerged from integrated systems that reflected American industrial philosophy, fundamentally different from Japanese manufacturing traditions. But military pressure allowed no time for gradual development or careful testing that proper engineering demanded. The reverse engineering effort began with fragments. Pieces of shot-down B-17s recovered from Pacific battlefields, incomplete technical drawings captured from abandoned American installations, and intelligence reports that described flying fortress performance without explaining how Boeing's engineers achieved those capabilities. Matsumura's team worked with information gaps that would have paralyzed less desperate efforts. What they discovered challenged everything Japanese aviation had believed about strategic bomber design. The B-17 structure represented engineering compromises that sacrificed theoretical efficiency for practical durability. Where Japanese designers optimized for minimum weight and maximum performance, American engineers had built redundant systems that maintained functionality despite component failures. The Flying Fortress carried 2,000 pounds of equipment that Japanese design philosophy would have eliminated as unnecessary complexity. Engine selection presented the first insurmountable obstacle. The B-17's four Wright R1820 Cyclone engines each produced 1,200 horsepower, generating combined power output that no Japanese engine could match. Nakajima's most advanced radial engine, the HI 109, delivered only 850 horsepower under optimal conditions. Installing four HI 109s would provide 3,400 total horsepower, compared to the Flying Fortress's 4,800 horsepower. The mathematics revealed a performance deficit that no amount of structural refinement could overcome. Matsumura calculated the implications with slide rule precision that offered no comfort to military planners demanding immediate results. Reduced power meant lower service ceiling, shorter range, smaller bomb load, and decreased defensive capability. The Japanese bomber would carry 60% of the B-17's payload to targets 40% as distant, while operating 5,000 feet lower where enemy fighters could intercept more effectively. Manufacturing constraints created additional problems that compounded engine limitations into systematic design failures. Japanese aluminum production was insufficient for bomber construction on the scale that strategic warfare demanded. Steel substitution added weight that further reduced performance while creating structural integrity problems that Japanese metallurgy couldn't solve with available materials and manufacturing techniques. The prototype that emerged from Nakajima's workshops in August 1942 represented Japanese engineering skill applied to impossible specifications under impossible deadlines. Designated Key 77, the aircraft possessed external similarities to American B-17 design, but lacked the integrated systems that made Flying Fortress capabilities possible. 4 engines, high wing configuration, defensive gun positions, all the visual elements that military observers expected from strategic bomber design. Ground testing revealed problems that wind tunnel analysis had predicted, but military pressure had forced engineers to ignore. Structural vibration at engine operating speeds created fatigue stress that would destroy airframe components during extended flight operations. Weight distribution caused control surface flutter that made precise flying impossible at combat altitudes. Most critically, the underpowered engines could not lift the fully loaded aircraft to operationally useful altitudes. Test pilot Lieutenant Commander Saburo Hayashi approached the Key 77's first flight attempt with professional skepticism earned through 15 years of evaluating experimental aircraft that looked impressive in photographs, but failed basic aerodynamic requirements when subjected to real-world flight testing. His engineering education provided mathematical framework for understanding why the numbers didn't add up to successful bomber performance, despite external appearance that suggested Flying Fortress equivalence. December 18, 1942. Fusa Airfield outside Tokyo. Morning mist hung over the concrete runway as ground crews prepared the Key 77 for its maiden flight. While Matsumura watched from the control tower with growing dread about what his team had created, under impossible pressure to deliver American performance with Japanese resources and timeline constraints. Hayashi completed his pre-flight inspection with methodical precision that masked growing concerns about what he was being asked to prove airworthy. The Ki-77's control surfaces felt sluggish during ground checks, responding with mechanical reluctance that suggested aerodynamic problems no amount of pilot skill could overcome. Engine run-up procedures revealed power curves that peaked well below design specifications, confirming his suspicions that Japanese manufacturing had created an aircraft that looked like a bomber, but lacked the fundamental capabilities that strategic warfare demanded. The takeoff attempt began at 0730 hours with Hayashi advancing throttles to maximum power, while ground observers held their breath and prayed to ancestors who had never imagined warfare conducted at 30,000 feet above Pacific battlefields. 4 Ha-109 engines roared with mechanical fury that sounded impressive to untrained ears, but delivered insufficient thrust for the aircraft's excessive weight and aerodynamic inefficiencies that Japanese engineering had been unable to solve. Ground roll extended far beyond calculated distances as the key 77 struggled to achieve flying speed against physics that cared nothing for Imperial ambitions or military deadlines. 1,200 meters elapsed before the aircraft reluctantly lifted off, climbing with agonizing slowness that demonstrated the fundamental mismatch between American performance requirements and Japanese industrial capabilities under wartime resource constraints. Matsumura watched through binoculars as his creation barely cleared the tree line at the runway's end, understanding that this marginal performance represented the key 77's maximum capability under ideal conditions with minimum fuel load and no combat equipment. Operational requirements would demand takeoffs with full bomb loads, maximum fuel capacity, and defensive ammunition that would transform today's barely adequate performance into complete operational impossibility. At 3,000 feet altitude, the aircraft's limitations became undeniably apparent. Engine temperatures exceeded safe operating parameters as cooling systems designed for lighter aircraft struggled with the thermal load of sustained maximum power operation. Oil pressure fluctuations indicated bearing stress that would cause mechanical failure during extended flight operations. Most critically, the bomber's rate of climb degraded to less than 200 feet per minute, making it impossible to reach altitudes where strategic bombing missions could be conducted safely. Radio communications crackled with updates that confirm Matsumura's worst engineering fears. Service ceiling appears limited to 18,000 feet maximum. Engine number 3 showing thermal distress indicators, flight controls becoming increasingly unresponsive as altitude increases. Rate of climb insufficient for operational requirements. The flight test continued for 43 minutes before engine failure forced an emergency landing that nearly destroyed the prototype and would have killed Hayashi if Japanese pilot training hadn't emphasized emergency procedures that American aviators took for granted through superior aircraft design and manufacturing quality control that prevented most mechanical failures before they became flight emergencies. Post-flight analysis revealed systemic problems that extended far beyond individual component failures into fundamental engineering decisions that had been compromised by resource limitations, timeline pressure, and incomplete understanding of how American bombers achieved their superior performance through integrated design philosophy rather than simple horsepower specifications. Engine analysis showed that sustained high-power operation created thermal stress patterns that Japanese metallurgy couldn't withstand. Cylinder head temperatures had reached 280 degrees Celsius, well beyond the Ha-109's design limits, causing expansion that degraded compression ratios and reduced power output precisely when maximum performance was most critical for mission success. Structural inspection revealed fatigue cracks in wing spars that would have caused catastrophic failure during combat maneuvering or severe weather encounters. The aluminum shortage had forced engineers to use steel reinforcements that created stress concentration points, where dissimilar metals expanded at different rates under temperature cycling, weakening the airframe through metallurgical incompatibility rather than design deficiency. Weight calculations demonstrated the impossible mathematics that had doomed the project from conception. The Ki-77 weighed 32,580 pounds empty compared to the B-17's 36,135 pounds. But Japanese engines produced only 70% of American power output, while Japanese manufacturing quality added structural weight that American production methods avoided through superior industrial processes and material science. Colonel Yamamoto received Matsumura's technical report on December 23rd, reading conclusions that confirmed his private fears about Japan's inability to match American industrial capability through reverse engineering efforts that lacked the fundamental infrastructure necessary for strategic bomber production. The numbers were unforgiving. Maximum bomb load 2,100 pounds versus the B-17's 4,800 pounds. Combat radius 800 miles compared to 2,000 miles for flying fortress missions. service ceiling 18,000 feet against the American bomber's 35,600 feet operational altitude. More significantly, manufacturing time requirements revealed the economic impossibility of strategic bomber production under Japanese wartime conditions. Each Ki-77 required 47,000 man-hours to complete compared to Boeing's 55,000 man-hours for B-17 production, but Japanese manufacturing efficiency was constrained by material shortages, skilled labor limitations, and quality control problems that American mass production had solved through industrial standardization and specialized tooling. The strategic implications became clear through mathematical analysis that offered no comfort to military planners who had demanded American capabilities without American resources. Japan could theoretically produce one Ki-77 for every 3 B-17s that Boeing manufactured, but the Japanese bomber would carry half the payload to targets one-third as distant, while operating at altitudes where American fighters could intercept effectively. By January 1943, intelligence reports confirmed that American B-17 production had reached 16 aircraft per day, while Japanese manufacturing struggled to complete one Ki-77 prototype per month. The industrial disparity that Admiral Yamamoto had feared was becoming strategic reality that no amount of tactical brilliance or operational courage could overcome through conventional warfare. General Hideki Tojo received briefings that painted an increasingly desperate picture of Japan's technological position relative to American industrial mobilization. While Japanese engineers struggled to copy single bomber designs, American factories were producing flying fortresses, liberators, Mitchells, and Marauders in quantities that would soon overwhelm Japanese air defenses through sheer numerical superiority, backed by superior individual aircraft performance. The Ki-77 program officially ended in February 1943 after the second prototype suffered catastrophic engine failure during climb testing, killing test pilot Captain Hiroshi Nakamura and destroying the aircraft in a crash that symbolized Japan's inability to bridge the technological gap between imperial ambition and industrial reality under wartime conditions that demanded immediate results from incomplete engineering. Matsumura stood in the wreckage-strewn hangar where twisted aluminum fragments represented 3 years of desperate engineering effort reduced to scrap metal and broken dreams. Captain Nakamura's death had transformed technical failure into human tragedy, forcing Imperial General Headquarters to confront mathematical reality that no amount of willpower could overcome. The Ki-77 program's cancellation carried implications that extended far beyond aircraft development into fundamental questions about Japan's ability to sustain technological warfare against American industrial capacity. The investigation into Nakamura's crash revealed systemic problems that made continued development impossible, rather than merely difficult. Engine mount failures had occurred at precisely the stress loads that combat operations would routinely demand, indicating fundamental design flaws that couldn't be corrected through minor modifications or improved manufacturing techniques. Japanese metallurgy simply lacked the industrial infrastructure necessary for producing reliable high-power aircraft engines under wartime material constraints. Dr. Jiro Horikoshi, designer of the legendary Zero fighter, was summoned to evaluate what remained of Japan's strategic bomber aspirations. His reputation as the Navy's most successful aircraft engineer carried weight that might salvage something useful from the Ki-77's technical wreckage. But 20 years of aircraft design experience had taught him to recognize impossible specifications when military pressure demanded miracles from inadequate resources and compressed development schedules. The technical briefing Horikoshi received on March 15, 1943, painted a sobering picture of American bomber capabilities that Japanese intelligence was finally beginning to understand through systematic analysis rather than wishful thinking. B-17. Flying fortresses were conducting daylight bombing missions over Germany from altitudes exceeding 25,000 feet, operating in formations that concentrated defensive firepower while maintaining precision bombing accuracy that Japanese aircraft could never achieve. More troubling were reports of American manufacturing efficiency that reduced B-17 production time to an average of 13.6 days per aircraft through assembly line techniques that Japanese industry couldn't replicate without completely restructuring manufacturing processes. Boeing's Seattle plant alone was producing more strategic bombers monthly than Japan's entire aircraft industry could manufacture across all categories during the same period. Horikoshi's analysis confirmed what Matsumura's team had discovered through painful experience. The B-17's capabilities emerged from integrated engineering systems rather than individual component superiority. American engines, propellers, hydraulics, electrical systems, and structural elements worked together through design coordination that Japanese manufacturers couldn't achieve while operating under resource limitations and timeline pressures that precluded proper development testing. The structural engineering that allowed flying fortresses to absorb battle damage while remaining airworthy represented manufacturing quality control that Japanese industry couldn't maintain under wartime production quotas. American aluminum was consistently pure, welding techniques were standardized across multiple production facilities, and quality inspection procedures eliminated defective components before they reached final assembly. Japanese manufacturing struggled with material inconsistencies that created structural weak points throughout finished aircraft. Engine technology presented the most insurmountable obstacle to strategic bomber development. Wright's Cyclone engines achieved their 1,200 horsepower output through metallurgical advances that Japanese industry couldn't reverse engineer from captured specimens. The precise alloy compositions, heat treatment procedures, and manufacturing tolerances required for reliable high-power operation demanded industrial capabilities that Japan simply didn't possess, despite 20 years of aircraft engine development. Horikoshi's recommendations, delivered to the Army Air Service in April 1943, acknowledged mathematical reality that military leadership had refused to accept. Japan should abandon strategic bomber development entirely and focus remaining resources on defensive fighters that might delay American air superiority long enough for negotiated peace settlement. Continuing the Key 77 program would waste materials, skilled labor, and engineering talent that could be applied more effectively to aircraft designs within Japanese industrial capabilities. The response from General Headquarters revealed the disconnect between military ambition and engineering reality that characterized Japanese wartime decision-making. Orders arrived demanding immediate resumption of strategic bomber development using alternative approaches that would overcome previous technical difficulties through superior Japanese fighting spirit and innovative design solutions. Colonel Yamamoto found himself assigned to evaluate captured American aircraft for exploitable weaknesses that Japanese engineers could turn into tactical advantages. The B-24 Liberator that arrived at Fusa Airfield in May 1943 represented the latest American bomber technology. Shot down over Rabaul with battle damage that had killed 3 crew members but left the aircraft structurally intact, enough for detailed technical analysis. The Liberator's examination revealed engineering approaches that differed significantly from B-17 design philosophy, while achieving comparable performance through alternative technical solutions. The high aspect ratio wing configuration provided better fuel efficiency at the cost of structural complexity that made manufacturing more difficult. Consolidated aircraft had solved this problem through specialized tooling and assembly techniques that Japanese industry couldn't replicate without massive capital investment in new production equipment. Tricycle landing gear represented another American innovation that Japanese engineers had dismissed as unnecessarily complex compared to conventional tailwheel configurations. But operational analysis revealed significant advantages during ground handling, takeoff, and landing operations that improved safety margins while reducing pilot workload during precisely the flight phases where crew fatigue and stress created the highest accident rates. Most significantly, the B-24's bomb bay design demonstrated American commitment to operational flexibility that allowed the same basic airframe to serve multiple mission roles through modular equipment changes. Bomber, transport, reconnaissance, and maritime patrol versions could be produced on the same assembly line, with components swapping that maximized manufacturing efficiency while meeting diverse tactical requirements. Japanese aircraft design philosophy had always emphasized single-purpose optimization that created superior performance within narrow mission parameters but prevented operational adaptability. The Zero fighter exemplified this approach, achieving unmatched maneuverability through structural weight reduction that made the aircraft vulnerable to battle damage and unsuitable for roles beyond air superiority combat. By summer 1943, American bomber formations were conducting regular missions over Japanese-occupied territories with impunity that demonstrated complete air superiority throughout the Pacific theater. B-17s and B-24s operated from Australian and New Guinea bases at altitudes where Japanese fighters couldn't intercept effectively, carrying bomb loads that systematically destroyed Japanese infrastructure while remaining beyond the range of effective defensive response. Intelligence reports described American bomber production reaching levels that defied Japanese understanding of industrial capacity. The Willow Run plant in Michigan was completing one B-24 Liberator every 63 minutes through assembly line techniques that treated 4 engine bombers like mass-produced automobiles. Combined production from Boeing, Consolidated, Douglas, and other manufacturers exceeded 1,000 heavy bombers monthly with quality control that maintained combat effectiveness despite unprecedented production volumes. The strategic mathematics became undeniable through accumulated evidence that American industrial mobilization had achieved objectives that Japanese planners had believed impossible. United States aircraft production in 1943 would exceed 85,000 units across all categories, while Japanese manufacturing struggled to complete 16,000 aircraft under increasingly severe material constraints and skilled labor shortages. Matsumura received orders in August 1943 to begin development of the Ki-91, a simplified strategic bomber that would achieve B-17 performance through revolutionary design approaches that overcame Japanese industrial limitations. The specifications demanded 4,000-pound bomb load delivered to targets 1,500 miles from base, while maintaining defensive capability sufficient for unescorted daylight operations. The engineering team assembled for the Ki-91 project understood they were being asked to perform miracles with resources that had proven inadequate for previous strategic bomber attempts. Material allocations were reduced compared to Ki-77 development, while timeline requirements demanded first flight within 8 months. Quality control standards were relaxed to accelerate production, despite evidence that manufacturing defects had caused the previous program's catastrophic failures. Design work began with attempts to reduce structural weight through elimination of non-essential systems that American bombers carried as standard equipment. Oxygen systems were simplified beyond safe operational limits. Electrical power generation was reduced to minimum requirements that left no reserves for battle damage or equipment failures. Defensive armament was limited to 5 machine guns compared to the B-17's 13 gun installations. Engine selection remained the fundamental problem that no design innovation could solve. Japanese manufacturers had developed no power plant capable of matching Wright Cyclone performance, forcing engineers to plan 4 engine configurations using available HA-109 radials that would provide 3,400 total horsepower, compared to American bombers' 4,800 horsepower output. The performance deficit would limit bomb load, operational altitude, and defensive capability below levels necessary for strategic bombing effectiveness. Yet, prototype construction began in October 1943, using manufacturing techniques that prioritized speed over quality control. Welding procedures were abbreviated to meet production schedules, despite metallurgical evidence that proper heat treatment required time that project timelines couldn't accommodate. Aluminum components were fabricated with reduced thickness margins that saved weight while creating structural integrity problems under operational stress loads. Adds. The Ki-91's first engine run-up test in December 1943 revealed cooling system inadequacies that had plagued previous strategic bomber attempts. Japanese radial engines generated more waste heat per horsepower than American designs, while Japanese cooling technology couldn't dissipate thermal loads effectively during sustained high-power operation. Engine temperatures exceeded safe operating limits within minutes of reaching maximum power settings. Test pilot Major Kenji Yanagimoto approached the Ki 91's maiden flight with professional resignation rather than optimism. 3 previous experimental bomber programs had ended in crashes that killed experienced pilots while failing to achieve operational capabilities that strategic warfare demanded. His engineering background provided mathematical understanding of why Japanese industry couldn't bridge the performance gap between Imperial ambitions and available resources. Ground testing revealed control surface problems that made precise flying impossible under conditions where strategic bombing required formation coordination and accurate navigation over extended ranges. Wing loading exceeded optimal parameters while power loading remained inadequate for maintaining formation discipline during combat operations. The aircraft would be unable to keep pace with faster American bombers during joint operations, even if basic airworthiness could be achieved. January 12, 1944. Fusa Airfield. The Ki-91 prototype sat on frozen concrete while ground crews completed pre-flight preparations under grey skies that seemed to mirror Japan's increasingly desperate strategic situation. American B-29 superfortresses were beginning operations from Chinese bases, carrying bomb loads that exceeded anything Japanese strategic bombers could theoretically deliver while operating from altitudes that Japanese fighters couldn't reach. Yanagimoto's takeoff attempt began with throttles advanced to maximum power as 4 Ha-109 engines strained against aerodynamic and gravitational forces that demanded more thrust than Japanese engineering could provide. Ground roll extended beyond safe limits as the overweight bomber struggled to achieve flying speed against mathematical certainties that no amount of pilot skill could overcome. The aircraft finally lifted off after consuming 1,800 meters of runway, climbing with barely adequate performance that demonstrated fundamental limitations rather than operational capability. Rate of climb measured less than 150 feet per minute at gross weight, making it impossible to reach altitudes where strategic bombing missions could be conducted safely above enemy fighter interception capabilities. At 8,000 feet altitude, engine number 2 began showing thermal distress indicators as cooling system inadequacies created temperature conditions that would cause mechanical failure during extended operation. Oil pressure fluctuations indicated bearing problems that Japanese metallurgy couldn't prevent under high-stress conditions that American engines routinely withstood through superior materials and manufacturing quality. The test flight lasted 37 minutes before multiple system failures forced emergency landing procedures that nearly destroyed the prototype, while demonstrating that Japanese strategic bomber development had reached technological limits that wartime resources couldn't overcome. Post-flight analysis confirmed that the Ki-91 represented the maximum capability achievable with available Japanese industrial capacity under existing material and manufacturing constraints. Engine teardown revealed metallurgical failures that had become grimly familiar to Japanese engineers struggling against American industrial superiority. Cylinder head cracking occurred at stress levels that Wright Cyclone engines routinely exceeded during combat operations. Japanese steel alloys lacked the molecular composition necessary for sustained high-temperature operation, creating thermal expansion patterns that destroyed compression seals and reduced power output precisely when maximum performance was most critical. Matsumura stood beside the disassembled Ha-109 power plant, studying metal fragments that represented 3 years of desperate engineering effort, reduced to evidence of systemic industrial inadequacy. Each cracked cylinder told the same story. Japanese manufacturing could produce engines that looked identical to American designs but lacked the fundamental metallurgical properties that made reliable high-power operation possible under combat conditions. The wing spar inspection revealed structural failures that extended beyond individual component problems into comprehensive design philosophy differences between Japanese and American aircraft engineering. Stress concentration points had developed at precisely the load distributions that strategic bombing missions would routinely encounter during formation flying, combat maneuvering, and weather penetration that operational requirements demanded from military aircraft. Colonel Yamamoto received the technical analysis on February 8, 1944, reading conclusions that confirmed his growing understanding of why Japan's strategic bomber programs consistently failed despite enormous resource allocation and engineering talent that had previously achieved remarkable success with fighter aircraft development. The mathematics were unforgiving and culturally neutral in their assessment of industrial capability gaps. Japanese aluminum production could supply material for 200 strategic bombers annually, while American factories were completing 300 heavy bombers monthly through manufacturing processes that treated 4-engine aircraft like mass-produced consumer goods. The quantitative disparity represented more than simple production volume differences. It revealed fundamental industrial philosophy variations that determined technological capability under wartime resource constraints. Quality control analysis demonstrated problems that extended throughout Japanese aircraft manufacturing rather than affecting only strategic bomber development. Statistical sampling of engine components revealed metallurgical inconsistencies that created reliability problems across all aircraft categories. Bearing failures, cylinder cracking, and cooling system inadequacies affected fighter production as severely as bomber programs, but shorter mission durations and lower power requirements made these deficiencies less immediately catastrophic. Dr. Horikoshi's final assessment, delivered to Imperial General Headquarters in March 1944, acknowledged strategic reality that military leadership had refused to accept through 2 years of failed bomber development programs. Japan lacked the industrial infrastructure necessary for strategic bomber production regardless of engineering skill, resource allocation, or development timeline extensions. American manufacturing superiority represented systematic advantages that couldn't be overcome through tactical innovation or operational courage. The recommendation carried implications that extended far beyond aircraft development into fundamental questions about Japan's ability to sustain technological warfare against American industrial mobilization. Continuing strategic bomber programs would waste materials, skilled labor, and engineering talent that could be applied more effectively to defensive systems that might delay American victory long enough for negotiated settlement rather than unconditional surrender. Military response demonstrated the institutional disconnect between strategic reality and operational planning that characterized Japanese wartime decision-making throughout the Pacific conflict. Orders arrived demanding immediate development of the key 94 Ultimate Strategic Bomber that would achieve American B-29 performance through revolutionary engineering solutions that overcame previous technical limitations through superior Japanese innovation and manufacturing efficiency. The specifications defied engineering logic while demanding impossible performance from resources that had proven inadequate for less ambitious projects. Maximum bomb load 8,000 pounds delivered to targets 3,000 miles from base, while maintaining defensive capability sufficient for unescorted operations over heavily defended American installations. Service ceiling 40,000 feet with cruise speed exceeding 350 miles per hour, using available Japanese engines that couldn't achieve these parameters individually, much less in 4-engine configurations. Matsumura found himself assigned to lead engineering teams that understood they were being ordered to violate physical laws through design innovation that military leadership believed could overcome mathematical constraints. 25 years of aircraft development experience had taught him that successful engineering required honest assessment of available resources rather than wishful thinking about technological breakthroughs that might emerge from desperation and timeline pressure. Engine development consumed 6 months of intensive effort that produced marginal improvements in high 109 performance through modifications that increased complexity while reducing reliability under operational conditions. Peak power output increased from 850 to 920 horsepower through supercharger modifications that created thermal stress patterns beyond Japanese metallurgy's ability to withstand during sustained combat operations. Manufacturing trials revealed production problems that made mass production impossible, even if engineering challenges could be solved through unlimited development time and resources. Specialized tooling required for engine modifications demanded machine tool imports that Allied blockade had made impossible. Skilled labor requirements exceeded available personnel after 3 years of military conscription that had removed experienced craftsmen from industrial production. By June 1944, American B-29 superfortresses were conducting regular bombing missions over Japanese home islands with impunity that demonstrated complete technological superiority throughout the strategic bombing realm. Operating from altitudes exceeding 30,000 feet while carrying bomb loads that surpassed anything Japanese aircraft could theoretically deliver, the Boeing bombers represented industrial achievement that Japanese engineering had proven unable to match despite enormous resource expenditure. The strategic situation had evolved beyond questions about Japanese bomber capability into survival concerns for Japanese industrial infrastructure under systematic American attack. B-29 formations were destroying aircraft factories, engine plants, and research facilities with precision that eliminated future development possibilities, regardless of theoretical engineering solutions that might emerge from continued strategic bomber programs. Intelligence reports described American bomber production reaching levels that defied Japanese comprehension of industrial capacity. The Boeing plant in Wichita was completing B-29 superfortresses faster than Japanese factories could produce fighter aircraft while maintaining quality control standards that ensured combat effectiveness, despite unprecedented manufacturing volumes. Combined American bomber production exceeded Japanese aircraft output across all categories by margins that made tactical resistance increasingly futile. August 15, 1945. Emperor Hirohito's surrender broadcast crackled across Japanese airwaves while Matsumura stood in the bombed ruins of Nakajima's Musashino plant, staring at twisted metal that had once been Japan's final strategic bomber prototype. 3.5 years of desperate engineering effort lay scattered across concrete floors, testament to the mathematical impossibility of copying American industrial supremacy through reverse engineering and imperial determination. The KISS-77, K-91, and K-94 programs had consumed resources that might have equipped 1,000 fighters, killed Japan's best test pilots, and proven that technological warfare demanded more than engineering skill and national will. America's sleeping giant had awakened with production capacity that transformed B-17 flying fortresses from impressive aircraft into mass-produced weapons of industrial warfare, while Japan's most talented engineers discovered that some performance gaps couldn't be bridged through innovation alone. In the end, Japan's attempt to copy America's strategic bombers revealed a fundamental truth about modern warfare. Victory belonged not to the nation with the most elegant designs, but to the industrial system that could manufacture reliable weapons faster than enemies could destroy them.